Upthrust can be defined as an upward force experienced by objects in a fluid. Upthrust can be defined as an upward force experienced by a body in a fluid or by an object in a fluid. An example of this force which we know is using a balloon, placing a balloon in water. When you place that balloon in water, when you try suppressing that balloon in water, you discover that there's a heavy force. It's quite difficult. It goes into the water. There's something pushing it up. That's always making it come up. So that kind of force is referred to as upthrust. Okay. Now, another definition of upthrust is that upthrust can also be defined as the loss weight experience. Upthrust can also be defined as the loss in weight experienced by an object. Upthrust can also be defined as the loss in weight. As a loss in weight experienced by an object partially or completely immersed in a fluid. Partially or completely immersed in a fluid. Partially or completely immersed in a fluid. So that means we could say the weight is equals to the upthrust. Now, for an object, the weight is equal to the upthrust. That's for an object partially or wholly immersed in a fluid. Now, I got to establish the last time that the bucket of water inside the well, the bucket of water inside the water in a well is lighter than when it is out of it. Now, when we consider the bucket of water placed in the well, it's more lighter, but when you start dragging it up, it becomes more heavier. Okay. We also established the fact of Archimedes Principle that states when a body is partly or completely immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. Now, that brought us to what we said, that the weight of the upthrust is similar to the weight of the fluid displaced. Now, when we talk about, now we know that the weight of the fluid, W is equals to mg, and density is equals to mv. Density is equals to, that's rho, is equals to m over v. So that means, let me share, let's see something. Oh, what's happening? Okay, can you see this? Okay. Now we know W is equals to mg, rho is equals to m. No, what's this? Is equals to m over v. Now, if we have that understanding, that means if we have that understanding, that means m is equals to rho v, but we know m is equals to rho v. Oh, let's come back. Coming. Now, from here, we know that m is equals to, now we know that m here is equals to rho v. Now, from this part, if w is equals to mg, that means, therefore, w is equals to rho vg. Okay, we can establish this, right? You understand this part, right?
Yes, sir.
Okay. Now, if that's the case, that means we know that the upthrust is equal to the density multiplied by the volume. That's rho is the density, v is the volume, and g is the acceleration due to gravity. Okay, the rho is the density of the fluid, the v is the volume of the liquid displaced. Now we know just from what we said that density is the ratio of mass of a body to its volume. Density is the ratio of mass of a body to its volume. That we've established that law. All right, let's come into, okay, please write the unit for density. The unit for density is kilogram per meter cube, kilogram per meter cube, or gram per centimeter cube. The unit for density is kilogram per meter cube or gram per centimeter cube. All right. If that's the case, now let's talk about relative density. Relative density. Okay, what is relative density? Please write this. Relative density of a substance is the ratio of the density of the substance. Relative density of a substance is the ratio of the density of a substance to the density of water. To the density of water. Another thing you should write, you should note there is that it has no unit. It has no unit. It has no unit. Okay? Now, it can be determined by estimating the density of the substance in kilogram per meter cube, dividing it by 1,000. All right, so please write this now. Relative density is equal to density of a substance divided by the density of water. Density of a substance divided by the density of water. Okay, we have another definition to this. We can also write that the relative density is the ratio of the mass of the substance. Relative density is equal to the ratio of the mass of the substance to the mass of the equal volume of water. Now, I said is defined as a ratio of the mass of the substance to the mass of the equal volume of water. That's mass of a substance divided by the mass of the equal volume of water. Okay, let's look at relative density of a liquid. Relative density of a liquid. The relative density of a liquid can be defined as the ratio of the upthrust experienced by an object, upthrust experienced by an object in the liquid to the upthrust experienced by the object in water. The ratio of the upthrust experienced by an object in the liquid to the upthrust experienced by an object in water. Okay, before we go into any calculation now, Let's look at the principle of flotation. Let's consider the principle of flotation. Okay, yeah, I gave it to you as an assignment. So can you tell me what states the principle of flotation?
When a boat displaces a weight of water equals to its own weight.
Sorry, I didn't get that.
The principle of flotation is when a boat displaces a weight of water equals to its own weight.
When the what?
When a when any boat displaces a weight of water equal to its own weight.
Okay, okay. That's similar also. Now, the law of flotation states that for a body to float in a liquid, states that for a body to float in a liquid, it must displace an amount of fluid. It must displace an amount of fluid equal to its own weight. Equal to its own weight. Okay. Now, what we are trying to say is that the weight of the object is equal to the weight of the fluid displaced. We have done that severally. We have watched that severally. Let's see if we could see, just to remind ourselves, if we could see that again. Okay, let's just see. It's still something based on Archimedes principle. So let's still see something of such again. Okay. Eureka. That's most times when Archimedes does something, he just shouts, Eureka! He got it. Okay, let's just see something on this.
When you think of Archimedes' Eureka moment, you probably think of this. As it turns out, it may have been more like this. The Sicilian city shows Archimedes of unprecedented scale. Chiron commissioned a city 50 times bigger than a city of Ocean. Named the Syracuse after his city, Chiron wanted to construct the largest ship ever, which was destined as a present for Egypt's colony. But could a boat the size of a palace possibly float? In Archimedes' day, no one. It was like asking, can a mountain fly? King Chiron had a lot riding on that question. Hundreds of workmen were to labor for years on constructing the Syracusia out of beams of pine and fir from Mount Etna, ropes from hemp grown in Spain, and pitch from France. The top deck, on which 8 watchtowers were to stand, was to be supported not by columns, but by vast images of Atlas holding the world on his shoulders. On the ship's bow, a massive catapult would be able to fire 180-pound stone missiles. For the enjoyment of its passengers, the ship was to feature a flower-lined promenade, a sheltered swimming pool, and bathhouse with heated water, a library of statues, a temple to the goddess Aphrodite, and a gymnasium. And just to make things more difficult for Archimedes, Chiron intended to pack the vessel full of cargo.
Wow.
400 tons of grain, 10,000 jars of
Jesus
pickled fish, 74 tons of drinking water, and 600 tons of wool. It would have carried well over 1,000 people on board, including 600 soldiers, and it housed 20 horses in separate stalls. To build something of this scale only for that to sink on its maiden voyage, well, let's just say that failure wouldn't have been a pleasant option for Archimedes. So he took on the problem. Will it sink? Perhaps he was sitting in the bathhouse one day, wondering how a heavy bathtub can float, when inspiration came to him. An object partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. In other words, if a 2,000-ton Syracusia displaced exactly 2,000 tons of water, it would just barely float. If it displaced 4,000 tons of water, it would float with no problem. Of course, if it only displaced 1,000 tons of water, well, Chiron wouldn't be too happy. This is the Law of Buoyancy, and engineers still call it Archimedes Principle. It explains why a steel supertanker can float as easily as a wooden rowboat or a bathtub. If the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, whatever is above the keel will remain afloat above the waterline. This sounds a lot like another story involving Archimedes and a bathtub, and it's possible that's because they're actually the same story, twisted by the vagaries of history. The classical story of Archimedes' Eureka and subsequent streak through the streets centers around a crown, or corona in Latin. At the core of the Syracusia story is a keel, or corone in Greek. Could one have been mixed up for the other? We may never know. On the day the Syracusia arrived in Egypt on its first and only voyage, we can only imagine how residents of Alexandria thronged the harbor to marvel at the arrival of this majestic floating castle. This extraordinary vessel was the Titanic of the ancient world, except without the sinking. Thanks to our pal Archimedes.
Okay, now with this, can you tell us, or can you explain? Have you heard about the Titanic?
Yes.
Why did it go down? Why did you think, or why do you think it's really went? What was now the Titanic was actually very big one, very big one. So why did Titanic sink?
It was floating at first, but after it hit the iceberg, maybe
Sorry?
the Titanic actually floated at first, but after it hit the iceberg, maybe it made the ship to lose some weight. Thereby, the ship was not displacing a greater amount of water to the weight.
I like you started. I like where you started from. You started from a layman's. Now, because I'm actually saying this because you have been taught Archimedes principle. Now, okay, let's just see. Let me see if I could see some facts, or we could learn something about Titanic. Because with this now, this should just explain to us why Titanic sank. Because it's now that we've learned now that we've learned what they call it, Archimedes principle, we should be able to study one of these things. We should be able to study why. So what happened to Titanic? What could have happened? Because it was one of the biggest ship of that time. Okay, let's just see this, and I guess you would have inspirations probably to know what to say. The sinking of the Titanic in 1912. All right.
The sinking of the Titanic, 1912. The luxury British passenger liner RMS Titanic began construction on March 31st, 1909 in the Harland and Wolff shipyard in Belfast, Ireland, and was completed 3 years later in 1912. As one of 3 Olympic-class ocean liners, it was designed to be the largest luxury passenger ship in the world and would cost $7.5 million to build. It had a length of 882 feet 9 inches, or 269.1 meters, a height of 175 feet, or 53.3 meters, and a width of 92 feet 6 inches, or 28 meters, and 26,328 tons. Below the waterline was the orlop decks for cargo, and the tank top where the engines, boilers, turbines, and electrical generators were. At the very top was the boat deck, where the bridge and wheelhouse were, as well as the lifeboats. In between were the decks for passengers with first, second, and third class cabins. The level of luxury was so high that second class was comparable to first class on any other ship. The 2,240 passengers would be from all walks of life, from millionaires and celebrities to poor immigrants looking for a better life in America. The ship would act like a floating hotel, featuring a grand staircase which allowed first-class passengers to move from deck to deck, and had a domed skylight to allow natural light in. The ship also featured a gymnasium, dining saloons, a reading room, a barber shop, a squash court, a Turkish bath, and a swimming pool. The ship carried 20 out of a possible 64 lifeboats. Therefore, there were only enough for half the ship's population. However, this was within legal requirements. Lifeboats were only intended for carrying passengers to rescue ships and not keep the entire ship population afloat. As a result, the company who owned the Titanic, White Star Line, felt complacent enough to keep the number of lifeboats low so the deck wasn't cluttered. Many claimed the Titanic was unsinkable because its hull was divided into 16 watertight compartments. It was said that if up to 4 of these flooded, the ship would still stay buoyant. All of these qualities drew the press to frequently talk about the new passenger liner. Disaster. In the morning of April 10, 1912, passengers began boarding the Titanic in Southampton, England, with large crowds gathering to watch the ship depart. At noon, the Titanic set sail under command of Captain Edward Smith, beginning her maiden voyage. It would stop at Cherbourg, France, and then Queenstown, Ireland, to pick up more passengers, and then begin its journey across the North Atlantic Ocean towards New York City. On April 14, 1912, warnings were coming in of icebergs from other liners, so Captain Smith had plotted a new course and continued to steam at full speed, which was standard practice. As it became dark, the temperatures were dropping to below freezing, and there was no moonlight or waves, making it difficult to see approaching icebergs. At 11:40 p.m. ship's time, the ship's lookout, Frederick Fleet, spotted an iceberg from the crow's nest. He rang the warning bell and telephoned the officers at the ship's bridge, shouting, "Iceberg right ahead." Fleet had spotted the iceberg with his eyes, as the crow's nest binoculars were locked away. The key's owner, Officer David Blair, had been removed from the Titanic's crew at the last minute and forgot to hand over the key.
Wow.
The officers on the bridge quickly turned the ship away from the iceberg, but it was too late. The Titanic grazed the iceberg along its side, ripping several holes in its hull below the waterline, with fragments of ice hitting the deck. At first, everyone felt relief. The lookouts and the passengers didn't even feel the collision. 11:50 p.m. Captain Smith and the ship architect, Thomas Andrews, went to inspect the damage. They knew the ship would start sinking, and by this time, 6 of the watertight compartments at the front of the ship's hull were already breached and began flooding. 12 a.m. The captain sent out a distress call over the radio in the hopes that there were other ships nearby, and gave the order for the Titanic's passengers to board the lifeboats. He knew there were only enough for half the population of the Titanic. At 12:25, lifeboats began their loading, with women and children first, as this was the protocol at sea. Many passengers still did not understand what was going on, and confusion and disorganization meant that the first lifeboat to leave had only 28 women and children aboard, when it could carry 65 people. First Officer Murdoch took the order to meet women and children first, then men if they were there, while Second Officer Lightoller took it to mean women and children only. The Carpathia, which was 58 miles away, heard the distress call and began sailing towards the sinking Titanic to rescue the passengers. Distress flares were shot into the sky to help locate the sinking Titanic. By 1 a.m., with the lower decks flooding, the bow of the ship began to sink below the water's surface. Water was pouring in 15 times faster than it could be pumped out, which was not helped by the fact that many of the passengers had left their portholes open and its propellers in the air. Chaos set in as lifeboats were running out. Some people pushed their way to the lifeboats, while others accepted their fate. They gave up their space. Archimedes did not want to survive the disaster and be branded a coward back home. By 2:05 a.m., the last lifeboat had left, but 1,500 people were left on the ship. The deck was now at a steep height, and many passengers fell into the freezing, icy waters. At 2:17 a.m., the captain announced, "Every man for himself." The stern gave way under the pressure and broke off, with the front half disappearing to the bottom of the ocean. At some point, Captain Smith went down with the ship, a maritime tradition that the captain would do in accepting responsibility for all on board. Some say he went to the wheelhouse and waited for the end, while others say he committed suicide using a pistol. The stern, smashing into the water's surface, became level and soon started to fill with water, sinking nearly 4 kilometers beneath the surface of the ocean. Many died as a result of drowning, but the main cause of death was hypothermia in the freezing waters, which occurred within minutes. Some of the lifeboats returned, but only 4 survivors were found. At 3:30 a.m., the distress flares from the Titanic were spotted by the Carpathia. The Carpathia arrived to the scene at 4:10 a.m. and picked up the lifeboats. Only 705 passengers would survive the disaster, with over 1,500 people losing their lives.
Okay. Wow, that was a pathetic story. Very, very pathetic. Oh God, I felt like crying. So tell me. So can you now tell me? Can we now let's explain what happened in the Titanic? Let's explain. We've been taught flotation. I've been taught Archimedes Principle. Wow, that was really. I've watched the real video, the Nollywood movie on this, but really, I think this one was really touching for me. All right, so tell me, what do you think happened? What explain?
Um, as the Titanic hit the iceberg and the water started entering into the ship, made the ship heavier. So
Good,
it was not this was displacing less more water.
beautiful,
But
beautiful. That's awesome. Yeah, wow. I was just seeing so many loopholes from the guy that handed over the key, okay, that was removed from the crew, and then out of maybe anger, he did not hand over the key, so they could not use the binoculars. From not using the binoculars, now these guys could not see the iceberg in front. Now, what really made the Titanic to sink was, apart from the fact that it hit the iceberg, that was not the major thing. Immediately, if they are taking responsibility of, oh, if it hits the iceberg, that means some parts will be dripping in water now, making the ship more heavier because it was no more displacing equal amounts of water anymore. So the upthrust was becoming lesser, the ship was becoming heavier. So it was really, really on the verge of sinking. Now, they ignored simple droplets of water coming into the ship. And the passengers on their own part, they left some of their portholes open. So water was already coming in, and no water was really going out. It was just coming in since they were in the middle of the ocean. So the Titanic was just an example of little drops of water make a mighty ocean. That was just an example of that. So it was really, really, really painful for them. They've taught us that the story of the Titanic became a known story, and has helped us as in physics, helps us in physics. Okay, let's talk about the principle of flotation. Okay, we've talked about the principle of flotation, that for a body to float in a liquid, it must displace an amount of fluid equal to its own weight. The Titanic was displacing less amounts of fluid, and more amounts of fluid was coming in, so it was no more displacing it anymore. And because of that, it could and it could not. Okay, I want to ask you, can you swim?
Yes.
So tell me, really, how come you can swim? As in, how come you see a fat person swimming, and yet somebody that is not fat cannot swim? What's happening to the upthrust? What's really happening? I need to understand what's happening. Why is that somebody can swim, another person cannot swim, and yet they are the same weight? Is it that those that can swim have holes in their body that they are displacing liquid out? Why those that cannot swim don't have holes? What's happening? I don't understand. Can you explain that? I'm waiting.
I cannot explain it.
You said what?
I cannot explain it.
Wow, that's a project for you. That's a project for you, actually. Because seriously, we are all humans now. Why can't somebody be able to swim? Another person is, we just talked about amount of liquid displaced. So what's happening? Okay, that's number one assignment too. Okay, let's look at the application of the principle of flotation. Application of the principle of flotation. The application of the principle of flotation. Number one, hydrometer. Hydrometer is used in hydrometer. Number two, submarine is used in submarines. Number three, we use it in the ship or boat. We use it in ship or boat. Number four is also used in hot air balloon. Hot air balloon. And number five, floating iceberg. Floating iceberg. Okay, let's look at a question. Let's look at a question. Question is a body of mass 20 gram. A body of mass 20 gram appears to have a mass of 13 gram. A body of mass 20 gram appears to have a mass of 13 gram, 13 gram in oil and 12 gram in water. What is the relative density of oil? What is the relative density of oil? That's number one. Number two, what's the relative density of water? Okay, can you solve that question? Okay, maybe you can try that first. Okay, show me how you got your answer. Are you done?
Yes, sir.
Okay. Good. Remember the formula we used. The formula that will be used in this case is the formula. They said find relative density of oil, and when we're talking about relative density of a substance, we said is the upthrust of the substance, upthrust experienced by the body in liquid, that's the upthrust of oil, divided by the upthrust of water, of the same body in water. Okay, can you tell me what's the upthrust of water? Remember we said upthrust is the weight displaced. Is similar to the weight displaced. Okay, so a body of mass 20 grams appears to have a mass of this in oil and this in water. Okay, remember upthrust. Upthrust has to do with the original weight or the original mass. For us to get the mass of liquid displaced, it has to be the original one minus the one it appears to be. Now, if the body appears to have a mass in water of, if it appears to have a mass in water of 20 gram, okay, that's the mass. Now, they said in oil, it appears to have a mass of what? In oil. It appears to have a mass of what? In oil.
13 grams.
Sorry?
13 grams.
Okay. In oil, 13 grams. And appears to have a mass of, in water is what? 12 grams, right?
Yes.
Now, but this is the mass of the substance. Now, the upthrust of oil will be equal to this minus the mass of oil, that's 20 minus 13, and then the upthrust of appearing to be in water will be the M minus the MW, which is equals to 20 minus 12. Okay, 20 minus 13, it's 7 gram, right? And this is 8 gram. So that means that the relative density, which is the upthrust of the body experienced in the fluid, okay, that becomes over that of water experienced in water. Okay, that becomes 7 over 8. Now that's the relative density of oil, and the relative density of water would just be 8 over 8, which is 1. Remember, we said relative density has no units, so we leave it without units. Do you understand that, please?
Yes, sir.
Oh, sorry, have you copied that before I remove it?
Yes.
Okay. Let's check for another example. A metal block of density 900 kilogram per meter cube. A metal block of density 900 per meter cube weighs 60 Newton in air. Weighs 60 Newton in air. Find its weight when it is completely immersed. Find its weight when it is completely immersed in paraffin wax of density 800 kilogram per meter cube. 800 kilogram per meter cube. Now, the G, association due to gravity, is 10 meter per second squared. Okay. You said 14 points what?
16 Newton.
16 Newton. Okay. Show me, what did you do? Let me see.
Welcome to Android 101.
You did a good job, but let's consider some things. Let me go back to the question, please. Let's see if I could get the question. All right. A metal block, 900 kilogram per meter cube, weighs 60 Newton in air. Find its weight when it is completely immersed. When it is completely immersed in water. Okay, sorry, in a mass in a paraffin wax of density. Okay, now the first thing we'll do is if it has this density, having this density, we know we're going to equate, if it has this density, we're going to equate, we know that density is mass over volume. And if density is mass over volume, that means we could get, we could say the mass of the object is the density multiplied by the volume. And the mass of the object, okay, let's start solving. Let me come. Okay, you did something good here. Okay, let me just clean off this. From here. Okay. From here, we could just do, we could say density is mass over volume. Therefore, mass is equals to density times volume. Let's call this equation 1. They also told us that weight, it has a particular kind of weight. Now we could also say weight is equals to, sorry, mass is equals to the weight over G. Let's call this equation 2. Now we have the density. We don't know volume. We know weight. We have gram. I mean, we have the association due to gravity. So let's equating equation 1 and equation 2 together. We say the density that's of the substance, which is 900, is equals to this. Okay, from here, I want you to find the volume for me from here. I want you to find volume from here. You know what to do from here, right? This example we're doing is going to be you and I it's going to be our efforts together. You know what to do from here, isn't it? Oh, are you there?
Said PV is not meant to be equal to W or G.
So, sorry. W over G, please. That was a mistake on my part. W over G. You know what to do from here, isn't it?
Yes, sir.
Okay, so tell me, what is V?
One point seven seven times 10 to the power minus 3.
Sorry?
1.77 times 10 to the power minus 3.
Which is the same thing as 0.007, right?
Yes.
Okay, meter cube. All right. Now, if that's the case, remember that dense up thrust we established is equals to rho times V times G. Do you understand that?
Yes.
Okay, the up thrust in the liquid. Okay, now the up thrust in the liquid, if we establish that it is rho times V times G, now we can also get the up thrust of the liquid, because the up thrust of the liquid will be the density of the liquid multiplied by the volume we just calculated, multiplied by acceleration due to gravity. So what would that be now? What would be the up thrust now?
Fifty-six. So 56.
Sorry?
56.
Okay, 56 Newton. Now, but we know that up thrust is similar to weight loss. Up thrust is also similar to weight loss. Now, if from the question, if it weighs 60 Newton in air, now the up thrust of the liquid is 56. What they asked us, find the weight. Find the weight of the body. How do you think we will get the weight of the body when it is completely immersed in the paraffin wax of density? That would be up thrust is equals to the weight minus this. Okay. Now for us to get the weight of the body, the weight of the body will be the weight of the body in air minus the up thrust, which was in liquid, and that gives us the weight of the body, right? That becomes 60 minus 56, which gives us 4 Newton. Do you understand that?
No.
Sorry?
No.
Okay. Now this is what I mean. This is what I mean. Now, but you understand how we got this up thrust to be 56, right?
Yes.
Okay. Now, what the question that they asked was this: find the weight find its weight when it is completely immersed in a paraffin wax of density. Now, before it was immersed, it was 60 Newton in air, right? Now, we've been able to get the up thrust which is the weight loss. The weight loss of the body. That means it has the weight loss of the body. We've been able to establish that, okay, the weight loss is 56. Now, the question was, find the weight of the metal block when it is completely immersed. Now, find the weight of the metal block when it is completely immersed. So that means when the metal block, when it is immersed in the paraffin wax, they wanted us to find the weight of it. Remember, it has displaced 56 Newton. Remember what we said, that Archimedes Principle, that the weight of a body when it is completely or partially immersed in water or in a fluid, the weight loss is equal to the weight in this, that's the weight displaced. Now, it has been able to displace 56, which is the upthrust. It was able to displace 56 Newton, and it weighed 60 when it was when it was not in the paraffin. Now, the question now was this: find the weight of the body in the liquid, in the paraffin wax. So simple, that would just be the weight outside, which was 60, minus the weight displaced, which is 56, and that gives us 4 Newton. Do you understand that analogy?
Yes, sir.
Okay. So that is it. Let me see. Let's see. I'm looking for a question that will give you as assignment. Oh, right now they're writing WAEC. WAEC has started today. I was looking at the WAEC physics. Really, one of the WAEC physics was this moment we just did. Awesome. That's number one question. I think physics should be on Wednesday or Thursday. Awesome. And that means we are doing well. Yeah, they'll be writing chemistry on Tuesday. Today is math. And the chemistry, I guess I would see how to start teaching you some of those things they do in chemistry. Physics now, we've been able to do moments. And when I saw the question, I was just happy. I told myself, because I was taking some WAEC students, I knew this was the question you could do also, because many of those questions are giving you to solve as example and as assignment, and you've been doing well on them. Now, but the chemistry, I don't think I've really taught you any of those things, because it has to do with practicals. It has to do with practicals, titration. Have you guys studied titration in school?
No.
Okay. Not to worry. I think while we advance in this, I'll be taking you through the calculation aspect of those things, because that's where it would come up then. Okay. First and foremost, let me just quickly give you your assignments before I forget now. Let me just give you some assignments first before, as we continue. Number one, a piece of wood of mass 60 kg. Just write this somewhere. A piece of wood of mass 60 kg and density 600 kilogram per meter cube floats in water of density 100 kilogram per meter cube. Calculate Roman figure 1, the volume of water displaced by the wood. Roman figure 2, the fraction of the volume of the wood immersed in water. The fraction of the volume of the wood immersed in water? I'm trying to see this question again. Number 2, a pencil of mass 5 grams can be balanced horizontally. A pencil of mass 5 grams can be balanced horizontally on a knife edge at a distance of 3 centimeters from the plane end when a mass of 2.5 grams is hung from this end. Calculate the distance of the center of gravity of the pencil from this plane end. Calculate the distance of the center of gravity of the pencil from this plane end. Okay. Number 3. 2 boys of weight 400 Newton and 700 Newton sit at the end of a seesaw. Okay, 2 boys of weight 400 and 700 Newton sit at the end of a seesaw 4 meters long. Pivoted at the center. Pivoted at the center. What will be the position of the third boy whose weight is 600 Newton? In order to balance the seesaw? What will be the position of a third boy whose weight is 600 Newton in order to balance the seesaw? And the last one is when a mass of 50 grams is hung at the 5 centimeter mark, when a mass of 50 grams is hung at the 5 centimeter mark, of a uniform meter rule, the rule balances on a knife edge. The rule balances on a knife edge placed at the 35 centimeter mark. What is the weight of the meter rule? What is the weight of the meter rule?
So can you repeat the question?
Okay, repeat the question. When a mass of 5 gram is hung at the 5 centimeter mark of a uniform meter rule. The rule balances on a knife edge placed at the 35 centimeter mark. What is the weight of the meter rule? Did you get that, please?
Yes, sir.
Okay. I think I'm trying to see. I guess there is. Let me check. There's one more thing. If I'm missing out any points, any way up. Did I give you any question, any example like this? A meter rule is found to balance at 48 centimeter mark. Did I give you any example like that?
Yes, sir.
Okay, I give you, right? Okay.
Yes.
Why I said a meter rule is found to balance at 48 centimeter mark when a body of mass 60 grams is suspended at 6 centimeter, right?
Yes.
Okay. Trying to check. Okay. If that's the case, then I guess I have one more thing to show you. Let's see. Okay, I think one more thing on the Titanic, something, Archimedes coming. Trying to be sure I've shown you what I needed.
Hey, it's Professor Dave. Let's learn.
Showing you what I need to do. Okay. Okay, I guess we have something here. We could just do again. 2 things involved. All right. Still talking about what we just discussed. All right.
In chemistry, we learned about the phases of matter as being solid, liquid, and gas.
Are you seeing this, please?
Yes, sir.
Okay.
In this course, we have been focusing on the motion of solid objects, but there is much to be discussed in the way of fluids as well. A fluid is defined as any substance that can flow and alter its shape by virtue of its particles being able to move around with respect to one another. In a solid, particles are fixed in a lattice, which produces a definite shape, so solids are not fluids. But liquids and gases are fluids because the particles move freely, and fluids have certain properties that are important in physics. Certainly any fluid will exhibit some density, which is mass per unit volume, represented by the Greek letter rho, not to be confused with the letter P. But another important characteristic of a fluid is its buoyancy. This is the upward force that is exerted on an object by the fluid it is submerged in. You will be familiar with the buoyant force if you have ever tried to push a beach ball underwater. It is difficult to do because of the buoyant force that counteracts your applied force. But exactly Steel is very dense, but the air in all the cabins is not. So overall, the ship is less dense than water. If you crushed the ship up into a ball of equal mass, thus eliminating all the air, it would definitely sink. In this way, the buoyant force can be expressed as the gravitational force of the displaced fluid, which is equal to the mass of the displaced fluid times acceleration due to gravity. A floating object displaces fluid based on its mass, and a sinking object displaces fluid based on its volume. So apart from the buoyant force, Archimedes was also the first to understand that when an object, like a person, is submerged in water, the volume of the water displaced must equal the volume of the object submerged, regardless of its shape. Any object with a volume of 5 milliliters, when fully submerged, will cause the water level to rise in this graduated cylinder to a reading of 5 milliliters more than before. This is an impressive insight for someone from ancient Greece, which is why Archimedes famously jumped out of the bathtub shouting, "Eureka," meaning, "I have found it." This is an exclamation that will forever be associated with scientific discovery. Hopefully you will have some eureka moments of your own during this course. But for now, let's check comprehension.
Can you try this?
Yes.
Sorry?
Yes.
Okay. Okay, you understand what they did there? They used 9.8 instead of 10, right?
Yes.
Okay.
Thank
Okay, so if that's all, now